Chapter 16.1 from the Red Book talks about water in the air. So it talks not only about why there is water in the air and kind of how it gets there, but about the water cycle, and then it kind of gives us some vocabulary to understand how much water is in the air and kind of why this all matters. So why does condensation and humidity matter? How does it form clouds? How does it result in precipitation and affect our day-to-day weather? So as we kind of move through each of these chapters, right, 15.1 through chapter 16, etc., we're gaining an understanding not only for the day-to-day weather that we experience, but the climate that we live in, right? So North America and even in there, New England versus, the South and Florida, that kind of area. So why there's different climates. But it also impacts availability of fresh water. It impacts lots of other natural processes, such as runoff and rivers and streams, as well as drinking water and aquifers. And that can also play a part in larger global events and climatic events that happen all over the place. So this seems very detail-oriented, and there's a lot of notes here, but don't get thrown off by that. We're going to take some detailed notes, but then what matters is the big picture, okay? So we've talked about weather a couple times, and really it only helps if you're talking about weather versus climate. Weather and climate are very, very similar, right? When we talk about weather, though, we're talking about a particular place and time. We're talking about Boston on March 12th, or we're talking about, Lexington on March 12th. There might be different weather in Boston than in Lexington. However, when we're talking about our climate, Boston and Lexington being 20, 30 minutes away from each other are going to undergo or experience the same climate, the same general average weather at a, over a couple month period of time. It might be 10 degrees warmer or colder in Boston or a little bit windier or something like that. But generally, what we're talking about when we're looking at climate is over a 3 or 4 month period, what does the weather look like? And how does that match up against last year or the year before, looking at the same 3 to 4 month period? You can also look at climate over thousands of years. In contrast, weather is more even so than day to day, right? It's within a short period of time. You can talk about the weather on one day versus the next, but it's even more accurate if you talk about it at a particular time. So in this hour window, what was the temperature, what was the pressure, etc. So all of the reason that I spent a minute going over that is because in order to understand what the weather is, we need to understand kind of what goes into creating it. So the first step is the water cycle. And the water cycle, I'm going to zoom in here, is something that you probably studied many, many times since some younger grades. So I'm not going to go over all of this in great detail, but you can pause the video and fill in some notes if you need to. So the water cycle, just like we've discussed a lot of things in these, chapter 15 and 16, is a continuous flow. It never stops, and it doesn't happen step 1, step 2, step 3, but is happening all of the steps all at the same time, all over the place. So condensation is where water vapor, meaning water that is in the gaseous state, cools down into liquid droplets, and that happens when we see clouds form. So water that goes up into the air and has a bunch of liquid in it cools down, and that gaseous liquid, that gaseous water, then becomes liquid water. And that's when we see clouds. Evaporation is when liquid water changes into water vapor. So we studied this in the first couple of weeks of science class, right? So if you've got just some puddles out in the street, some of that is going to be evaporating because of the sun's energy up into the atmosphere. Eventually, if enough water goes up into the atmosphere and it cools down, meaning condensation, clouds will form up. Transpiration is eventually plants releasing water through their leaves. I always refer to it as plant sweat, right? So water gets sucked out of plants either intentionally, right? They can release water to cool themselves down just like humans do, or unintentionally, just like if you're sitting on a beach, you can get dehydrated. Precipitation occurs when rain, snow, sleet, or hail falls from the clouds. So if those clouds get enough liquid in them and it cools down enough so that it's not just water, tiny, tiny water droplets, but actual liquid water, so a drop of water, right? That could then form rain or snow depending on how it froze or potentially didn't. That liquid precipitation that hits the ground, whether it's snow or whether it's rain, it will flow across the land and into rivers, streams, there should be an R in that word, streams, and eventually into the ocean or into aquifers. Aquifers being freshwater storage places underground, not human created. So that is essentially, once again, talking about a big cycle of what happens to our water. And that is essentially what we're talking about when we're looking at the weather, right? We're saying, is it warm and therefore stuff is evaporating, or is it cold and potentially rainy in an area, right? What is happening at a particular place and time? So humidity is, especially in New England in the summers, is one of the most interesting pieces. This also has a lot to do with condensation and evaporation. So humidity is the amount of water vapor or moisture in the air. So how much liquid is being held by the air around us? And that is, of course, dependent on the temperature of the air, meaning that the warmer the air, the more water that air can hold on to. If the air is cold, it can't hold on to very much water. It's going to condense and potentially rain or snow. So why is this? Well, remember, warm air means lots of energy. Lots of energy means that those molecules can stay in a gaseous state and more liquid can be evaporated and held onto by the air. If the air does not have a lot of energy, then it's not going to be able to evaporate much water, and in fact, the water that's actually in the air at that time will lose energy. It'll condense, meaning it'll actually become more dense as it turns into a liquid state and potentially fall from the sky, right? It will not be able to stay as a vapor. It will be a liquid. And if that happens, it potentially rains. So relative humidity is essentially the amount of moisture in the air versus the maximum amount it can hold at a particular temperature. So let's say it's 70 degrees, right? I guess we're using Fahrenheit since I use 70, otherwise that would be really hot, Celsius. So if it's 70 degrees out, that's pretty warm. But let's say it's a really dry, warm day. That means you're going to have a low relative humidity. A 70-degree day, because it is warm out and the air therefore has a lot of energy, it could potentially hold on to a lot of water. But if for whatever reason at that time there's not much water in the air, you're going to have a low humidity day. That would be a low relative humidity. If, on the other hand, it has been hot for days on end, and therefore lots of evaporation has happened, right? The weather has been really nice, and it's just been evaporating water like crazy. That 70-degree day is probably then going to be relatively humid because there's so much water in the air. So essentially, relative humidity is kind of like what we are feeling at a certain time. If it is a low relative humidity, that means that the air doesn't have as much water as it could. And we're going to feel okay with that, right? It's not going to feel very humid and sticky out. If the relative humidity is high, that means that for that temperature, the air has almost as much water as it can hold, right? Which is when we go outside and we feel like we're just, like we feel wet without even being wet. It's all sticky out, right? And there's some math equations that you can do. You're just doing a division times 100 here, right? So how much water is in the air versus what's possible at its saturation point. Saturation meaning when it is at 100%, when there is as much water in there as possible. So water vapor versus temperature. If the temperature stays the same, relative humidity can change if more water vapor enters or leaves the air. What does that mean? So that means that if the temperature stays the same, right, your relative humidity could go up or down depending on if evaporation or condensation happens. Conversely, let's say that the amount of water stays the same, so evaporation or condensation does not change, but temperature could rise or drop and could change this equation here. So essentially, this whole thing right here is very confusing. And what it is saying is, how could you change this percentage number? Well, you could change that percentage number by either changing the temperature or by changing how much water is in the atmosphere. Because if you change the temperature, you're going to change what that total amount that the air could hold is, right? If you dropped the temperature, the air can hold less water. If you increase the temperature, it could potentially hold more water. So you're changing the denominator. Likewise, another way that you could change that percentage is by either adding or taking away water from the atmosphere. We're just essentially here looking at how you can manipulate that math. So you can measure relative humidity, and essentially that you do it by using the psychrometer, and it just measures how much water evaporates off of this wet bulb. If it's humid out, then it's not going to evaporate. If it's not humid out, then water would leave that and enter into the atmosphere. Okay? So essentially you're measuring how much water is evaporating off of this thing, and that tells you what the relative humidity is of the surrounding area. So the process of condensation. So this is where you watch water droplets on the side of a glass form. So picture it's summertime, right? You don't have to listen to Mr. Kalman talk. You're not watching this video. It's summer. You're at the beach, and you take out a nice can of cold soda, right? You brought a cooler with you to the beach. You've got a nice cold can of soda. You pull it out and you put it into the sand next to you, right? You're drinking it slowly. And after a few minutes, you realize that it's all, what we call sweaty, right? There's all of those droplets of water on the outside of the can. So now you wonder, where did that come from? Is that soda from the inside of the can? Is that water that something dropped on there? No, it's not from the inside of the glass. It's from the air around it. So if this is your can or cup of soda with a couple ice cubes in it, right? It's really, really, really cold in there. We're going to say cold. Out here, it's hot. So if it is hot out here, then the air has lots of little drops of water that are in gaseous state. As they touch the can or the cup that is really cold, what's going to happen to those energized water molecules that are in the vapor form? Well, they're going to cool down, they're going to lose energy, and they're going to condense out of water vapor into liquid water, and they're going to form drops of water on the side of your glass. And that's how you end up with a sweaty, quote-unquote, can of soda. So this happens when air has reached the dew point. Right? So the dew point is the temperature to which air must cool to become completely saturated, meaning that the air has cooled down and therefore it can no longer hold on to all of that water because it has lost energy. Right? If it starts out as energized air, it's going to hold on to liquid water, it's going to hold on to water as a vapor. As that air cools down, it loses energy. So if it loses energy, it's no longer going to be able to hold on to as much water vapor. Some of that water vapor is going to condense into liquid water. And when that happens, that's the drops of water there. We need to remember that warm air loses energy due to a change in temperature, which leads to condensation, right? Or drops of liquid water, right? And remember, that's not just forming out of nowhere. There was always that water in the air. We just couldn't see it because it was in the gaseous state. It was super energized and therefore floating around as a gas. But as it loses energy, it can no longer stay in the gas form and changes to a liquid form where it has condensed, right? So by cooling the air around it, because of the ice in this glass and how cold that glass is, you cool the air right here. You cool the air all the way over here, all the way over here, not really, right? Your glass of soda isn't that cold. It's not going to cool the air, 10 feet away. But it's going to cool the air on a microscopic level just around that glass. But changes the dew point, meaning it changes the temperature just enough that the water condenses out of the air into drops of liquid. So this is exactly how clouds form, right? As warm air rises, it cools down, causing that area of air to become saturated or hit the dew point, right? Same words there, and therefore condense, meaning the water vapor can then attach to dust or smoke or salt or can freeze into ice crystals if it's cold enough as it goes out of gaseous form into liquid and potentially solid form if it's that cold. So we don't really care about this stuff. Not that we don't care, but remember, in science class, it's not always about these details. So whether a cloud is cumulus, stratus, or cirrus doesn't really impact the concepts that we're trying to learn here, which is why air moves and why water will condense into clouds and how that impacts our weather. Whether a cloud is cumulus, stratus, or cirrus does give us hints about the weather that is coming, but we're more interested in the process of this. If you are super interested in this, you can know that the cumulus clouds are puffy white. You're going to have fair weather if they're puffy. Stratus is going to be, they're kind of those layered clouds, and they usually can indicate heavy continuous rain or some serious fog. Cirrus are thin, feathery. Sometimes means a storm is coming, right? If you've got stratus clouds, you've probably got a storm that's here or really close. Cirrus means kind of the precursor to that, right? And these are just altitudes. But again, this is not as important as it is about how they form and why they form in a part of the whole water cycle. So there's many different types of precipitation, and we know what these generally are, right? Precipitation is when water in liquid or solid form falls to the ground after it's been condensed. So that can happen as rain, snow, sleet, or hail. So rain is just liquid water drops, right? So water droplets increase in size more than 100 times into a droplet. So thousands of water molecules go into a water droplet. And then 100 times many water droplets need to form into a water drop. So that just gives you a concept of how many water molecules it takes to form a raindrop versus a water droplet. And I know those are they sound like kind of made up terms, right? But if you've just got, here are just water molecules as water vapor in the air, right? So let's say that I have hit 100 of those. 100 of those is going to form a water droplet. Now you need 100 of those water droplets, 1,000 molecules to form a water droplet. 100 times that to form a raindrop. So there is a ton of water molecules in one raindrop. Snow essentially forms when temperatures are so cold that water vapor changes directly to a solid. So that is the key point there. It doesn't go from the water vapor to a liquid and then from a liquid to a solid, but it just goes directly to a solid. Sleet is freezing rain, and it forms when rain falls through a layer of freezing air. So sleet is essentially rain that freezes on its way down. Rain that freezes on the way down. Hail, so essentially, forms from drops of air that carry raindrops to high altitudes where they freeze and combine through collisions, and that happens multiple times. So here's my cloud, right? And if I've got a drop, that's not a drop, if I have a drop of rain that then gets carried up here and freezes and combines with a couple other drops of rain, right? Whoa, that's a weird one. So they all get carried up and they all smash into each other. That's going to form a piece of hail. And that process might happen a couple times. And so the more times it happens, the more pieces of hail and more pieces of water drops are going to slam into each other. The more times that occurs, the more, or the bigger the hail is going to be. So as that happens multiple times, you can get really big sized pieces of hail if that happens many, many times. If it only happens once, you'll have relatively small pieces of hail. So essentially, rain is when the water vapor condenses into liquid form and then falls from the sky. Snow is when that water vapor changes directly to a solid. It doesn't turn to a liquid and then freeze. Sleet is when you've got rain and it freezes on the way down. And hail is essentially when you've got those raindrops that then within the cloud go through multiple iterations of freezing and combining into larger pieces of rain that continue to freeze again and again and form bigger and bigger ice balls, essentially. So this section in the book, just to summarize here, goes over initial steps of the water cycle. Obviously, there's a lot more that we can go into about evaporation and runoff, but it kind of goes into how does precipitation form and how does humidity form and how do those two things interact, right? So after evaporation occurs, when is it and how is it that clouds will form? And from there, when is it or how is it that those clouds might or might not result in rain? Because just because you look up in the sky and see clouds, right, whether it's kind of foggy clouds or whether it's big, fluffy white clouds or dark, ominous clouds, you may or may not get rain. And so understanding what has to happen for A, those clouds to form, and B, for those clouds to then release liquid as either rain or snow or sleet or hail is kind of a complex process. So that's what we learned about with condensation and the dew point, as well as how that relates to humidity. Remember, when we're talking about humidity, it's not just walking outside and feeling like there's a wet blanket out there because it's all sticky, but humidity has a big impact up in the stratosphere, higher up in the stratosphere, where it may or may not form clouds based on the humidity, and based on the relative humidity there, it may or may not eventually rain. And that all has to do with the dew point and that process of condensation. So really, this chapter is furthering our understanding of that water cycle and how weather is going to form at a particular place and time because of those convection cells and uneven heating and cooling of Earth.